Okay, let's get started. Good morning. Let me start by reminding you what we are trying to do. So our current goal is to prove this proposition 31, sorry. And so the goal is to obtain bounds on the operator norm of our Wigner matrix H. And this proposition shows that if you can prove that the norm is bounded by some arbitrarily large constant, so C can be any positive number which is fixed, then in fact the norm has to be very small. It has to be bounded by 2 plus an error term of order n to the minus 2/3. So this is what we are proving now. And for the proof, there's one important ingredient that we will use, that is this lemma 32 that we stated and proved last time. If you recall, the proof was very straightforward thanks to all the work we did in the previous section. This was just an analysis of the stability of this quadratic equation along with all the probabilistic estimates we derived in the previous section. So we will use this to prove proposition 31, and let me remind you of the idea. So this is still review. So the idea was so if you have an E, let's say an energy E, that's bigger than 2, such that, and you can find some eta, you have a free choice of eta, such that the imaginary part of G is much less than 1 over n eta, then E cannot be an eigenvalue of H. Because if there exists an I such that lambda I is equal to E, then the imaginary part of G at E. So what is the imaginary part in the spectral decomposition? It is equal to eta over E minus lambda j squared plus eta squared 1 over n. This is just the imaginary part of G. And now I can just estimate this. So this is a sum of positive numbers. I can estimate it from below by just one of them. And I pick the one where j is equal to I, in which case this first term is 0, and I get 1 over n eta. So in other words, the imaginary part of this Stieltjes transform of this empirical eigenvalue measure detects eigenvalues, and every eigenvalue gives you a positive contribution of size up to 1 over n eta and equal to 1 over n eta if E is precisely at the location of that eigenvalue. So what we are going to do, you can view this as establishing a spectral gap, a gap in the spectrum, so you cannot have eigenvalues between 2 plus this error term and C, and we will do that by taking any number E and showing that one can find an eta such that this holds with very high probability. So I think this is as far as we got last time, right? So this is the end of the review. So now the question is how to choose this eta will, of course, in general, we'll have to make it depend on E. So how does one, this is in fact easy to figure out. The conditions are easy to figure out, or there are at least few obvious conditions we need. So how are we going to get a bound on the imaginary part of G? All that we have at our disposal is the local law. So in other words, we can estimate the imaginary part in terms of G in terms of the imaginary part of M. So we estimate use the estimate imaginary part of G is equal to the imaginary part of M plus, I can call it G minus M. Okay, so far this is a triviality. And then, if you recall, we know very precisely how the imaginary part of M behaves. This is this elementary analysis of this simple solution of the quadratic equation. And this was done in lemma 15. In lemma 15. And in lemma 15 we showed that now we are outside of the spectrum. And in that case this thing behaves up to a constant. It behaves like eta over square root of kappa plus eta. And since I will assume always that, I will assume this condition, that kappa is less than or equal to eta. Sorry, greater than or equal to eta. So this behaves like eta over square root of kappa. And G minus M behaves like behaves like G minus M. So this is what we're going to use here. So we will, maybe I'll just leave it. So you see from this why we need this lemma 32, which outside of the spectrum is more precise than our theorem 11, the main local law. If you recall, theorem 11 says that this thing is stochastically dominated by 1 over n eta. Now this is correct, but this would be useless because this bound is not affordable. If we got this, if we estimated G minus M, if we replace this by 1 over n eta, we could do that, it would be correct, but then we would be dead. This argument would clearly fail because the goal is to prove that this thing is much smaller than 1 over n eta. So we can't do that. So we have to use this in the hope that if kappa is sufficiently large, all of these terms are in fact much smaller than n eta, and you can see it, right? In the extreme case, you can just stare at these terms. This is maybe instructive. In the extreme case where kappa is big, let's say kappa is 1, and eta is very small, eta is much less than 1, then each one of these terms is obviously much smaller than 1 over n eta. This one because you have a square root of eta, this one because you have an n eta to the 3/2, and this one because you have an n eta squared. So at least for kappa of sufficiently large kappa of order 1, this guy is obviously better than that, and therefore this argument should work. Whether it works all the way down to n to the minus 2/3 is a different question. One just has to check the estimates. We will see that it does, in fact. Okay, so we want this. We want the following condition. So therefore we need so what do we need? We need, well, I will make this assumption always that eta is less than or equal to kappa. We want both of these terms to be small. You see, we also want, of course, the imaginary part of M to be small, and therefore we want this term to be much less than 1 over n eta. And so you can, let me put things together. So if I put the eta to the other side and I take the square root, I find eta has to be much less than n to the minus 1/2 kappa to the 1/4. This is correct, yes. And then we, of course, also need G minus M has to be much less than n eta. So if we can guarantee, so this one is kind of trivial, but if we can guarantee these two conditions, then the argument will be complete. So now the rest of the proof is a completely elementary argument where we just have to verify these conditions individually for all of these terms. So let me be a bit more precise. There are these, this is, as I said, I use this notation only in these heuristic discussions. It's not quite clear what it means. I mean, informally, okay, I told you what I mean by it. This is much smaller than that. Or in other words, this divided by that tends to 0, and then tends to infinity. But we have to be a bit more precise. So now I start the actual proof. This was somehow to motivate and explain how the proof is going to go. So let epsilon be positive, and I will now assume this in fact will turn out to work if I assume this lower bound. So that's some lower bound I need an 8 epsilon, as it turns out. I mean, one could maybe make this 8 slightly smaller, but it really doesn't matter. Epsilon is some arbitrary positive number. Okay, and we will take these values of E. Now, as a remark, if you recall, our spectral, this is domain in which the local law holds. By choosing my parameter, I think it was called tau, sufficiently small, I can make my rectangle so big that I can include this whole region. For a given C, I can choose my rectangle large enough so that this region is included in my rectangle, and therefore this estimate holds. Okay, now I will define an eta, which is a function of E. How will I choose my eta? Well, I know how to choose it. I want to choose my eta to satisfy this condition. This I know I have to choose this, otherwise the argument is not going to work. So let me choose the largest eta that satisfies this condition. This much smaller than I translate into a factor of n to the minus epsilon. So I say that my eta is by definition minus 1 minus epsilon times kappa of E to the 1/4. Okay, so I often omit the arguments, but here I put them in. So everything depends on E. Kappa, of course, depends on E. It's just E minus 2. And this is how I choose my eta. And this choice is not surprising at all. It is the largest possible choice I can make. If I choose eta larger than this, I know this argument is not going to work. Okay, so in particular, so for the following, I mean, there's going to be just some basic algebra. So for the following algebra, it's helpful to keep in mind that this means if you square this equation and bring the n to the other side, you get the following relationship between kappa and eta. So let's now estimate the various factors appearing here. So this one is the easier one. So the imaginary part of m, we already know it's going to be much smaller than 1 over an eta. Let's redo this argument. We should get n to the minus epsilon if we chose our eta correctly. So this, as we saw, is bounded by C times eta over kappa. And well, what's eta over kappa? Eta over square root of kappa is, what's the easiest way to do that? I suppose the easiest way to do that is to start from this equation. So eta over square root of kappa, this is equal to C times 1 over n, 1 plus 2 epsilon times, maybe that's not what I want to do. Let me plug in the eta. It's probably easier to plug in the eta. Yes, so the eta. Well, there's something What's the easiest way to see this? Anyway, we know it has to be small, right? This is exactly how it shows things. Okay, this is bounded by n to the minus epsilon over n8.
2 epsilon.
2 epsilon? Okay, I'll leave this as an exercise. I mean, we did it here, we did the estimate here, right? You just have to check the factors of epsilon. Or should we do it? Maybe it's not. Okay, let's try to do it. It is a, let's see, so what is the, I mean, this is the answer that you will get. And so the condition came from here, right? So this one, let me write it, yes, so this is, I mean, it's the complete triviality, it's what I had here, right? So let me write it as something times 1 over n eta. So I have C times n eta, and then I have upstairs, I will have eta squared times n times square root of kappa. And this is precisely what I had, right? So eta squared. So I think, Renaud, what you said is correct. We probably get an n to the minus 2 epsilon. So eta squared times n over kappa is equal to n to the minus 2 epsilon. So this is C n to the minus 2 epsilon. Okay. So, so this is what, of course, what we wanted, but this was clear because that's how we chose our eta precisely to get this kind of bound. Okay, so that was easy. Now the less easy part is to check that all of these terms are much less than 1 over n eta. So I write this with very high probability. I get the following bound. Let me leave this lemma 32 on the board because I will use it. So we just have to plug in things and check that that we get the estimates we aim to get. So G minus M. It's actually quite convenient, it's just above. So let's see, G minus M. So I said with very high probability, which means I unpack the definition of this guy, I put in an n to the epsilon. So let me pull out, so I have this n to the epsilon, fine. And I will also pull out an n eta to make it easier to see what I'm doing. I pull out this n eta and then I want to make sure that everything in here is going to be very small, much smaller than n to the minus epsilon. Okay, so the first term, if I pull out an n eta, it means I pulled out the n already, and then what remains is an eta over square root of kappa, right? And then the second term, I pulled out an n eta. What remains is a kappa to the 1/4. Kappa to the 1/4. I pulled out an n and an eta, which means what remains is the square root of n eta. And then finally, this term, I still have a square root of kappa, and I pulled out one n eta, so I have another n eta. Okay, so this is using lemma 32. All right, now let me plug in the definition of kappa, and in fact I will replace eta with kappa, so I will just use this definition of eta. I will plug in my choice of eta. So I have n to the epsilon over n eta times. So eta over kappa is going to be, well, I just plug in this thing. Okay, so I think we can all do this. I replace eta by n to the minus 1/2 minus epsilon times kappa to the 1/4. And if I do this carefully, so I have a square root. And then let's look at the powers of n, maybe. So I will have an n to the minus 1/2. So I put that in the denominator, and then I will have an n to the epsilon from that one, and then I had a kappa downstairs, and I get a kappa to the 1/4 upstairs, which means I have a, let's see. Sorry, I have a kappa downstairs, and I have a kappa to the 1/4 upstairs, so I have a kappa to the 3/4 downstairs. Okay. So these exponents, they might seem slightly baroque, but in fact, it's important. They are important. I mean, you will see all of these terms are relatively borderline. So the exponents you have to keep track of the exponents carefully. Okay. Then the next one.
Isn't it going to the minus epsilon?
It is probably yes. Thank you. Yes, it's an n to the minus epsilon. I think that's correct. Good. Okay, then the next one. How should I write that? If I plug in an eta, maybe I'll just write up what, I mean, you can all check this. I mean, I did this carefully at home, and you can also do it carefully. And these two terms are absorbed into the same error bound if you plug in this. Okay, so you can. I think it's maybe you can check this in the pause if you wish, but this is what you get.
Shouldn't there be an epsilon over 2?
So there might be an epsilon over 2. Okay, all right, so let's check it then. It's good, you are all, you don't let me cheat. That's a good attitude. All right, so let's do this second one carefully. Let's do it maybe as a side calculation here. So I have a kappa so 1 over kappa to the 1/4, and then we have an n to the 1/2, and then we have the eta, which is n to the minus 1/4 minus epsilon over 2, and then I have a kappa kappa to the 1/8, I guess. Okay, so let's see. This, wait, maybe I forgot to, this goes in here, yes. Okay, so if I take a square root, then I think I get exactly this one here, right? So I think this is equal to that, right? This is kappa to the 3/8, so that's okay. And then I have an n to the minus, I have a negative exponent. So here maybe I want a plus epsilon. Right, I think if I want to get an upper bound, I probably need a plus epsilon here. And then I have an n to the 1/4, so this gives that guy here, and I think that was it. Okay, so that was this term here. And then this term here, I have
It's just the square of the term before.
it's the square of the term before, indeed. So here we are, yes. Mm-hmm. Good. All right. Okay, so this is what we get, and now we just have to make sure that these guys are indeed small. And now if you, maybe I can continue here. So these are, I mean, this is mental gymnastics. The difficulty is in setting up the things right, the problem right. But once you've set it up right, then you just have to follow through these estimates carefully. And now we know that kappa, so kappa to the 3/4, we know that kappa is greater than or equal to n to the minus 2 over 3 plus 8 epsilon. So I will use this. So using that kappa is greater than or equal to n to the minus 2/3 plus 8 epsilon, we get g minus m so we have n to the epsilon n eta. So, okay, so this, as Johannes pointed out, this guy is the square of that guy, so maybe let's just look at one of them. Let's look at this one. Let's look at the thing inside the square root. So we know that this is greater than or equal to, I can erase it now. You see, it's just juggling with these exponents, making sure that you're doing things right. So this thing here, so this thing, I have a lower bound on kappa, so I get an upper bound on the thing inside the square root, which is the same as that guy. And I get, so I have an n to the epsilon minus 1/2, n to the epsilon minus 1/2, and then I have minus 3/4 times that guy, which gives me plus, and 3/4 of times 2/3 is precisely 1/2, and then I have minus 3/4 of 8 epsilon, which is minus 6 epsilon. So this is n to the minus 5 epsilon. Okay. And this is also, of course, n to the minus 5 epsilon. I take the square root, so I can estimate this by n to the minus 4 epsilon if I wish. I take the square root, I get n to the minus 2 epsilon times this n to the epsilon, I get just n to the minus epsilon here. Okay. So, I mean, this was just chosen in such a way. I chose the 8 in such a way that these epsilons eventually become sufficiently negative. Yeah. But the key thing is that these kind of cancellations, so in other words, these terms really are all small under this assumption here. This is what you need. This is in fact sharp. This is the best you can hope for. And now we are basically done, right? So let's just summarize what we have proved. So the conclusion is that we have established that this imaginary part of G is much less than 1 over n eta. And that means we cannot have an eigenvalue at E. Very high probability. The imaginary part of G of E I get maybe a 2 because I estimated this in 2 steps. I had the imaginary part of M, and then I had the absolute value of G minus theta. So that's what I have obtained. Now a remark, I will not dwell on this. We've seen many instances of this, is that this bound holds in fact simultaneously for all E. by the usual Lipschitz continuity arguments. Or if you want to, you could have said that this lemma 32 that we used holds simultaneously for all E. In fact, that's maybe an easier way of doing it. And then, so in other words, there is one event of very high probability such that all of these estimates hold simultaneously on that event. So for all E which is less than or equal to C and bigger than or equal to 2 plus n to the minus 2/3 plus 8 epsilon. And therefore, H has, with very high probability, no eigenvalue in this interval. And that's the end of the proof. Okay, so this epsilon, of course, was an arbitrary positive number. So we can...
I think in the second line you wanted to have simultaneously somewhere.
I probably did, thank you, yes. So holds simultaneously, yes. Holds simultaneously. Okay. Good. So that establishes this bound. It establishes a spectral gap. And what we have to do now is to prove that prove an unconditional result, or in some sense, this is, if you wish, this spectral gap, you can view it as a conditional result, that if the bound is smaller than C, then it is in fact much smaller, it's optimal. And we have to make sure that the bound is in fact, that the norm is bounded by some constant C. And you've done the exercises, so you know how this goes, at least if H has sub-Gaussian entries. So before stating the next proposition, if H had sub-Gaussian entries, and if you recall the problem set that you worked on this week and last week, we would be done, right? Because there you proved using this net argument that the norm of H is bounded by some constant C with very high probability. This net argument is it's a powerful argument used a lot in various areas, notably in high dimensional geometry and analysis of Banach spaces and so on. It has the advantage of giving a relatively simple proof of this fact. The problem is that this constant C that you get, you can track it through this argument. The C is not going to be optimal, and there's no way of making the C close to 2 with that argument. So we need to do this in 2 steps. This is the step that gives you the optimal bound, assuming you know that you have some rough bound. And the rough bound you can prove relatively easily for sub-Gaussian entries. And now the question is, one could ask, well, what if the entries are not sub-Gaussian? And that's this proposition I'd like to do. So the proof is a nice argument. It's an interpolation argument. The interpolation arguments are very powerful. They are used a lot in probability theory, in particular in random matrix theory. And the idea is that you want to prove something, and you know how to prove it for one model, and you would like to prove it for another model. And you create some continuous bridge between these two models, and you follow how the property you want to prove, how this changes along this continuous bridge. And if you manage to prove that it doesn't change much or at all, then you are done. So it's you can view this also as a continuity argument. It's somewhat similar to the bootstrapping argument that we used, except it's much simpler. So I would like to explain how this goes. So first, if H has sub-Gaussian entries, the proof is obvious from proposition and exercise 29. So exercise 29 is the exercise where you had a series of exercises where you analyze properties of sub-Gaussian random variables, and then in the end you did this net argument, which is a very powerful idea, and you got this this bound proof that H. So this was exercise 29, provided H has sub-Gaussian entries. Okay, so the question is, what happens if H does not have sub-Gaussian entries? And there we can do a very simple interpolation argument. So how does that go? We will define a continuous path in the space of random matrices that connects our H, that we would like to understand, to another random matrix that I will call W, that is also a Wigner matrix and that has sub-Gaussian entries. And I would like to construct this path in such a way that every point on the path is a Wigner matrix. So let's and also so I want this matrix to be independent of H. So I mean, this is a very simple sort of trivial coupling. So I take my probability space to be the product of these two spaces. I just choose these two matrices to be independent. And then we define. So the definition is very plain. It's basically a convex combination, right? So how do you, if you are in the space of matrices, you want to go from matrix A, let me maybe use small letters W, in a general linear space, if you want to go from W to H in a straight line, then you would define H of T to be equal to T times H plus 1 minus T times W, right? This would be your interpolation. T is a number between 0 and 1, so H of 0 is equal to W, and H of 1 is equal to H. Now, this kind of convex combination for the space of matrices has a problem, which is if I do this, the intermediate matrices are not Wigner matrices. Does anyone see why? So if I defined, let me start by writing something that I will not use. So this is going to be wrong. 1 minus T H plus T times W. Let's see, now which way around do I want to? So if T is 1, sorry, I would maybe like to do it the other way around. I want to do it the same way as here. So T times H plus 1 minus T times W. Okay. So we have to satisfy, I would like to make sure that for all t between 0 and 1, this is a Wigner matrix. If t is 0, then I get W. If t is 1, I get H. So that's fine. If t is anything in between, let's check the assumptions. Is this matrix, are the entries centered? Do they have 0 expectation? The answer is yes. Now, if you recall, we also want their variances to be equal to 1 over n. And this is the problem. So we can compute the expectation of h ij of t squared. This is equal to, so I write this as a, okay, let me write it in a few steps since this is an important observation. So this is h, so it's t times hij plus 1 minus t times wij squared. Okay, now I just multiply out the product, and the cross terms, they vanish, right? Because these are mean zero random variables, and they are independent. That's why I want to have independence. So if I do this, I get t squared expectation of hij squared plus 1 minus t squared expectation of wij squared. And this is 1 over n, and this is 1 over n, because these were Wigner matrices. So the variance I get is t squared plus 1 minus t squared, and this is not 1. So that's my problem. However, the problem has a very simple solution. Here, instead of having t squared plus 1 minus t squared, I would like to have t plus 1 minus t. So I will cancel the squared here. I will put in the square root here, and I will be happy. So that's what I do. And this now is a Wigner matrix by the calculation I just did. And you can check as an easy exercise that the higher moment assumptions also hold. They are just inequalities, so they can be checked just by the binomial theorem. Okay, so this is a Wigner matrix. So this is for t. So then, by this calculation that we just did, so it's a Wigner matrix for all times between 0 and 1. Okay, now what I will do, you see the argument is extremely straightforward. What I will do is I will say that at time 0, I know h of 0 is w and has sub-Gaussian entries, and therefore its norm is bounded by this 2 plus order n to the minus 2/3. And then I will make a very small step in t. In fact, I will make steps of order 1 over n squared. And then I don't know quite what happens to the norm. I know, however, I can estimate this function has a certain Hölder continuity in t in the norm, because I have some extremely rough norms on the rough estimates on the norm of h. I might not know it's bounded by c, but I can certainly say that it is bounded by square root of n, or even n. There are some very trivial arguments you can do to do that. I will give you one right now. But provided you know that, let's say, the norm of h and w is bounded by square root of n, if I make a step of size 1 over n squared in t, I will be able to conclude that, that in one step, the norm of h of t cannot change by too much. And if it was smaller than this number, and I know that for all t I have this gap, it has to remain smaller than that. I have a gap which I'm not allowed to cross, so here's my... This is a gap. I start here. I'm not allowed to cross this gap. I'm not allowed to be in the gap, ever, for any value of t. I make a small step, and this brings me in somewhere in this interval. However, I know I'm not allowed to be here. So after the step, I have to be here. And then I make another small step, and I always remain to the left of this bound. And eventually I reach 1, and that's how the argument will be concluded. Okay, so I will do this precisely, and that's basically the end of the argument. So it's a very easy thing. I would like to do it carefully, and for that maybe I need a bit more time than we have left now. So let's do a break, and I will finish this after the break. Okay, so let me, in order to do this interpolation step, let me explain to you how we estimate the norm of one such step. Now, there are many relatively rough ways of estimating norms. I would like to give you one which is in fact quite precise. We wouldn't need such level of precision, but it makes the argument a bit simpler, and it's something you should anyway know. It has, I think it doesn't have a universally agreed name. In the literature, I and many other people call it the Schur test, and it's the following. You may have seen it already. So what does the Schur test say? It says that the operator norm of a matrix, so the operator norm with respect to the L2 norm, so it's the L2 to L2 operator norm of a matrix, is bounded by, you take the maximum of the row sums and or the maximum of the column sums and this is a bound for the operator norm. It's not always sharp, but in many circumstances it is sharp. But there are many, of course, there are many matrices for which this is not sharp. The operator norm has the inconvenient feature of not having a simple expression in terms of the matrix entries, and this is a simple expression in terms of the matrix entries, and which is usually quite precise. When you can plug in a variety of matrices and see how accurate it is. For example, for the identity matrix, it's sharp, and you can plug in many other matrices, and it gives you relatively good bounds. You will see the bounds it gives us for Wigner matrix, for example, are far from sharp. They are off by a factor square root of n. So this is an exercise. So we get so let me take 2 times s and t. Let's say t is bigger than s. And let me estimate the operator norm of these two guys. And I just use the fact that the square root function is Hölder 1/2 function. So square root of x minus square root of y is bounded by square root of absolute value x minus y. So, and then I have the norm of h by the triangle inequality. Like that. Okay? And so let's apply the Schur test. So h and w are both symmetric, so these two things are the same, right? The row sums are the same as the column sums, so I can just take one of these guys. So this is going to be the maximum over I of sum over j hij plus maximum over I sum over j wij by the Schur test. And now I just use my assumptions on the entries. I will say that these guys are all stochastically dominated by n to the minus 1/2. Therefore, the sum is going to be bounded by n to the 1/2 plus epsilon, and let's say I estimate everything just by n. Okay, so I don't really care about the exponent, so I can estimate everything by n. So I know with very high probability the difference in norm between two nearby matrices h of t and h of s is bounded by square root of t minus s times n. So now I do the interpolation, so I do a proof. So formally this is a proof by induction. So we prove by induction so I take steps of size 1 over n squared that the norm of h, n over n squared, is bounded by 2 plus okay, so this is the argument by induction. So let's do it. So the start of the induction when n is equal to 0 is obvious, because h of 0 is equal to w. So n is equal to 0. So this is okay by proposition 31 and exercise 29. Since h of 0 is equal to w. Is that okay? Is that clear? I have a h of 0 is w, which has sub-Gaussian entries, and therefore we know that this holds. And then we just make steps. How do we go from n to n plus 1? So h of n plus 1 over n squared. So this is bounded by, so this is bounded with very high probability by h of n over n squared. So I compare this to h of n over n squared. So I get the norm, by using the triangle inequality, I get the norm of this guy plus the difference of the norms, which I estimated here. So it's square root of the difference of the times n. So it's square root of 1 minus n squared times n. And this is equal to 1. Okay, so I know that going from n to n plus 1, the norm can increase or change, but in particular increase by at most 1. So therefore this is bounded by so the conclusion is by induction assumption. Right, by induction assumption, this guy with very high probability, or this guy has a norm which is bounded by 2 plus order of n to the minus 2/3, I have a 1. And so I can choose my C to be equal to 4, and I deduce from this bound that in fact this guy must be bounded by 2 plus O n to the minus 2/3. So by proposition the claim now follows, since h of 1 is equal to h. So if I complete the induction and I arrive at little n being equal to capital N squared, and then I have reached h. Okay, so that was this interpolation argument. Is this okay? All right, so now we are done. So this was the proof of this proposition 31. Now I recall what we're actually doing. So the main result of this section was this eigenvalue rigidity result, which stated that lambda I minus gamma I and gamma I was defined like this, rho or infinity. Doesn't matter. Minus 1/2. Okay, so this was the definition. If you recall, this was what we had last time. This was the eigenvalue rigidity result. And the last time I wrote an infinity, I can write an infinity, it doesn't matter. So do you recall this? This was the eigenvalue rigidity result that we are trying to, so this was in parentheses, and this is what we were trying to prove. An important ingredient, in fact, the proof of this has two important ingredients, and we have now proved both. The first one says that, the first one is this, precisely. If I look at it, I apologize, I forgot the argument here. So the first one is this, that what we just proved, that this proposition 32, I think it was, that stated that that the operator norm of H is bounded by 2 plus order n to the minus 2/3. That was proposition 33 that we just concluded. And the other one is the semicircle law on small scales that we proved in the previous subsection. Now, putting these two things together, in fact, we will find relatively quickly, we will be able to prove this result here. So let's do that. So the result itself is a relatively straightforward consequence of what we already have. In order to do everything very carefully requires some, you have to do some writing, you have to make sure that you cover all possible cases. But the basic argument is not complicated with the tools we have now. So let me now prove Theorem 30. So what is the basic input? I will explain to you first roughly, what is the basic strategy. First, and this is my semicircle law. First, I will only work in the right half. So I will only consider eigenvalues with index I up to n over 2. If the index is bigger than n over 2, the argument is exactly the same. You just have to replace I with n plus 1 minus I and so on. So I will only work in this half here. And then what we know now, what we have at our disposal, is first of all, we know that the eigenvalues have to be located in this interval. So they have to be very close to this semicircle law. That's what we just proved, proposition 33. And the second information that we have is this semicircle law on small scales, is that if I take I count the number of eigenvalues, so they have to be contained in this interval here, and if I count the number of eigenvalues in any such interval, let's say a half infinite interval, the number of eigenvalues in here is very well approximated by the integral of the semicircle law. And these two things together will give this result quite quickly. I hope it's not too shocking, because these guys are both characterized by the counting function. In fact, lambda I is characterized by the same equation, up to maybe this 1/2 or something, where you replace rho by mu. And we know that rho is very close to mu. So that's roughly how the argument goes. So we only, now let's start the proof. So we only consider I less than or equal to n over 2. So the other ones are similar. So one thing, so I said that I would like to consider, I only consider the first n over 2 eigenvalues. I would like to make sure that these eigenvalues never go near this edge here, so that I'm always, you see, a priori they could fluctuate enormously. We haven't proved yet that they don't fluctuate like that. But I would just like to make sure that I'm at least not close to the left edge. And that's very easy to prove. So this is a preliminary observation. So by this semicircle law on small scales, which was theorem 29, we find that mu, certainly if I calculate the mass between -1 and infinity, this is with very high probability, so it's going to be close to the corresponding mass of rho, which is strictly bigger than 1/2. Right? I'm calculating the mass in this interval. The mass with respect to rho is strictly bigger than 1/2, taking more than half of the semicircle. And therefore, by the approximation in this is greater than or equal to 1/2 with very high probability. And what do we deduce from this? If we know that mu of this guy is bigger than or equal to 1/2, it means that lambda with the index 1/2, so I is equal to n over 2, is at least equal to -1. Okay, so there's some mental gymnastics where you have to translate bounds on counting functions to bounds on eigenvalue locations. That's just the monotonicity of these functions. Okay? So if the counting function, if you have a lower bound on the counting function, this kind of counting function, then you also get a lower bound on the corresponding eigenvalue. So lambda I is greater than or equal to -1 for all I less than or equal to n over 2 with very high probability. Okay? Because this says that at least half of all eigenvalues are greater than or equal to -1. Which says in particular that lambda n over 2 is at least -1, and therefore all there are eigenvalues with smaller indices. Okay, so that was a preliminary remark. Now for the actual proof. So let's, again, in order to work precisely we need to fix ourselves an epsilon for all of these estimates. And then we consider two cases. The first case is the case where we are very near the edge. So this is the case when we are not really using the shape of the semicircle distribution, we are just very near the edge. And I will call that case 1. And that is the case where both gamma I and lambda I are near the edge. So 2 minus n to the minus 2/3 so they have to be close to 2. We know that in fact they are. I could also replace this infinity with a 2 plus the same guy. Now I know that. Well, gamma I by definition is always bounded by 2, and lambda I by the proposition we just proved is bounded from above by this thing if you replace the minus with a plus. But for now we don't really care, we are interested in the lower bound. So this is a condition that I call star, and this is a condition that defines the case. So case 2 is going to be the logical negation of this condition star. Let's first deal with case 1. So by definition of gamma I, here it is. Here is the definition of gamma I. So I claim that in this case, if gamma I is greater than this guy here, I get an upper bound on the index I. So I think that I get an upper bound is clear, right? So remember gamma I gamma I is here. Gamma I is defined as the number where the integral of this region here is equal to I minus 2 over n. And if I know that gamma I is very close to 2, so it has this lower bound, I will have an upper bound on I, of course. And the upper bound that I get is, we have I is bounded by C n to the 3 epsilon. So why is that? Well, let's work this out carefully. So n to the minus 2/3 plus 2 epsilon. I said that this thing is an upper bound for 2 minus gamma I, right? I'm just rewriting this inequality. So gamma I is greater than or equal to 2 minus that guy here. And you know, and this in fact I gave as an exercise when I introduced these gamma i's, this is just, you just have to integrate the square root function. You have to know that when you integrate the square root function, you get, so the integral of square root of x is equal to x to the 3/2. And looking at this definition, you deduce, and if you recall, this was the little exercise, that 2 minus gamma I was of order I over n to the 2/3. Okay? You remember if you take this definition of gamma I. I mean, I will not do the exercise for you. It's a one-line exercise. You take this definition, I is less than or equal to n over 2. You take this definition, you plug in the semicircle law, which has a square root type behavior near this edge. If you integrate the square root, this thing will behave like 2 minus gamma I to the 3/2. And that's already the exercise solved. Right? That's what stands here. Okay, so from this, if you just read off this inequality, you will get that bound. Okay, so I know that I is at most n to the 3 epsilon. And I also know that lambda has to be close to 2. I know that lambda I minus 2. So I have a lower bound, which is this one here, and I also have an upper bound, which is the same. Okay, so the lower bound is by assumption here, and the upper bound is by proposition 33. And now we can put things together. So we have an upper bound for gamma I, which is trivial. So since gamma I, so by assumption is in 2 minus. So this was by assumption my lower bound on gamma I, and the upper bound is trivial. It's 2. Of course, these gamma i's are always less than or equal to 2. We get, now let's try to prove this claim. So we would like to estimate, I want to get this here. So now I'm working with I less than or equal to n over 2, so I can ignore the second factor. This is always the smallest one. So I just have to get n to the minus 2/3 times I to the minus 1/3. So here, I can't do anything smart. I'm just using the fact that both are close to 2. So lambda I minus 2 plus gamma I minus 2. And I know that both are bounded by this number here with very high probability. Okay. So I'm just using these estimates, and I would just like to ensure that this number is in fact bounded from above by that number. So I have an n to the minus 2/3 and n to the minus 2/3, and I would like to make sure that n to the 2 epsilon is less than or equal to I to the minus 1/3. So I want an upper bound on I, which is exactly what I have somewhere here. Where was the upper bound? Here. So let me write this up carefully. So I claim that this thing is bounded by C times n to the 3 epsilon n to the minus 2/3 I to the minus 1/3. Simply because n to the 2 epsilon, I would like to I know that my I was bounded by n to the 3 epsilon, and therefore this inequality is correct, maybe up to a constant c. Okay. And the epsilon was arbitrary, and therefore I obtained precisely this bound. So this, in some sense, was the sort of trivial edge case. You don't really see much. You don't see at all the behavior. You don't really see the behavior of the semicircle. We just had to deal with it because these are the edge eigenvalues. So let's do the more interesting case, which is that this does not hold. Which means that lambda I is less than that, or gamma I is less than this number. So how do we do that? Now this is the heart of the argument. I will define a function which is nothing but the counting function. It's the same counting function that we used before. So it's going to be rho of E so this is going to be my f. So by definition, let me make a few observations about f. I would like to compare. So the following calculation is really the heart of this proof, and if you do that, you kind of see how the proof has to work and why this result has to be true. I will start by expressing just the definition of gamma I, which in fact this one here, I will just rewrite this equation. So f of gamma I, and this factor 1/2 is slightly annoying, so let me keep it separately. 1 over 2n. So this is now equal to I over n, right? By definition of gamma I. And I also know, and this is how I make the link to the eigenvalues. This is equal to, I over n is equal to mu of the interval lambda I infinity. So these are two random objects, mu and lambda are random, but when I combine them like this, I get a deterministic number. And now I would like to go back to the f, so I would like to replace mu with rho. And I can do that. I have this semicircle law on small scales. So this was theorem 29. So this is equal to f plus let me call this equation sharp. So you see I have characterized, I have two things. I have f of gamma I equal to f of lambda I, and I have a very small error term, basically of order 1 over n. I mean, I have this guy which is unimportant, this guy which is the crucial error term, but it's very small. And if I know that f is sufficiently nice, regular, in particular, if I have bounds on the derivative of f, for example, I can just apply the mean value theorem, right? If you know that f of gamma is equal to f of lambda plus something small, and if you know that the derivative of f is bounded, then you know that gamma I must be close to lambda I. So it's just an application of the mean value theorem. So, of course, in order to apply the mean value theorem, we have to be a bit careful with derivatives. So let's do this in a few steps. Let's do it carefully. So by definition of f, I would like to make sure that f it cannot be too small, and that I basically ensure by saying that at least one of these two numbers has to be smaller than this quantity, 2 minus that guy. And therefore, at least one of the values of f either at gamma I or at lambda I has to be sufficiently large. So if I take the maximum, so this is not, so the negation of this, I know that at least one of these two guys must be bounded by must be bounded by this counting function evaluated at this point here. And again, the integral of the square root is x to the 3/2, so I get this number to the 3/2, and this is now equal to well, n to the minus 2/3 times n to the 3/2 gives me a 1 over n, and then the factors of epsilon, I have 3 factors of epsilon. I can maybe drop 1. I can drop 1 and to kill the c, and that's what I get. And then we can use sharp. So what have we deduced from this? I have 2 numbers, f of gamma I, f of lambda I. I know that one of them, at least, is greater than or equal to n to the epsilon times this number. I know also that their difference is bounded by this number. And therefore, they must be comparable in size, right? If their difference is much smaller than the largest of them, then they both must be, in fact, of the same order. So this I can write like this: lambda I, 1 plus order n to the minus epsilon. Okay? I can write it like that. Is this clear? This is just analysis 0 from when you were 12, or something like that. Okay, so this is already very helpful. I know that, in fact, now both of, a posteriori, I know that both of these guys are of the same size. And now I can estimate the derivative. Remember, I want to use the mean value theorem. The derivative itself can be a nasty object, but of course, the derivative of this function f is easy. So first, if we know that these f's are comparable, we know also that remember f was just the integral of this square root guy. So f of this guy behaves like 2 minus that guy to the 3/2. So since f of lambda is of order 2 minus lambda to the 3/2, we can just take this equation, take it to the power 3/2, and we will conclude that 2 minus gamma I is also of the same order as 2 minus lambda I. So we deduce that 2 minus gamma I is of the same order as 2 minus lambda I. So they are both at the same, approximately at the same distance from the edge. So now let's compute the derivative. So what is f prime at lambda? Well, f prime at lambda is by definition equal to the, maybe there's a minus sign. There's a minus sign, I think. It's by definition equal to the minus the derivative, well, minus the density of the semicircle wall. 2 minus lambda, 1/2. Is this okay? The derivative of f is just the density of the semicircle, which behaves like that. We deduce that the derivatives are also comparable. This is in general very much not true. If you have a function, you evaluate it at 2 points, which are sufficiently close. The value of the function is comparable. The values of the function are comparable, this does not imply that the values of the derivatives are comparable. In this case it does, simply because of these simple estimates. We deduce that these derivatives are comparable, and therefore, if I take any intermediate lambda, since the derivative is a monotone function, I will deduce that f prime of lambda is comparable to f prime of gamma I for any lambda any lambda between gamma I and lambda I. And now I can use the mean value theorem. So by the mean value theorem, I can finally derive an expression on the difference lambda I minus gamma I. So by the mean value theorem, this is equal to the difference in the values of f divided by the difference of the derivative at some intermediate lambda, which of course one never knows in the mean value theorem, but I know that no matter which lambda I choose, I always have the derivative, it's comparable to the derivative at gamma I. So this is now an explicit expression, and this I can evaluate. So I need an upper bound on this. So the numerator, if you recall, by star was precisely n to the epsilon over n. And f prime of gamma I is given, absolute value is given by this. And if you recall, gamma I was precisely we had an asymptotic expression for gamma I, which was this exercise. And if you plug that into this expression, you get I over n to the minus 1/3. Okay, so this was the 1 over f prime. Okay, simply from this expression, and then we had this asymptotic expression for 2 minus gamma I, which gives precisely this number here. And this is of course equal to c times n to the epsilon times with very high probability. And as always, my epsilon was arbitrary, and I've covered both cases and I got the same conclusion. Okay? So this was the end of this proof. This was the end of this application and the proof of this eigenvalue rigidity result. So you see that once you have this semicircle, the local semicircle law, then deriving these kinds of consequences, you just have to have the idea of looking at counting functions. That's it. And it's really this calculation. Once you do this calculation, it's clear. You have to use the mean value theorem. There's some cleaning up you have to do to make sure everything works as it should, but there's really nothing particularly hard going on. Okay, maybe this is a good point to stop. So I will stop here. Next time, I would like to give the last application, which is very easy. The proof is maybe 3 lines, but it's a very powerful application on the eigenvectors. And then I would like to move on to something completely completely different. So next time is also the beginning, the first half hour maybe of next time is going to be the final application, and then we're going to start something new. Okay, so I'll stop here now.